Hello everyone, welcome to the video. In this video, we're going to talking about the neural network model notation, and this will be preparation for our future video. So let's get started. So first, as example, we will draw a very typical neural network structure, and we will write all the basic notations there. And after we finish demonstrating the network structure, we will explain each of the notation in detail. And now we are drawing the uh, three-layer neural network model. And you can see this is a lot of work. I have to fast forward to save some time. So now we can see we have a neural network model here. And we will pause the video for 1 second. Explain to you a little bit. So basically, you can see we have a three layer here, and each neuron we put an N in the A inside the neuron, and also for each branch, there's a weight assigned there, and also there's a bias. I didn't draw there, but the default each neuron has a bias to add to the net input. And let's go ahead to the next step. So now I'm writing the calculation for each layer. This actually is a so-called forward calculation of the neuron. You can see if the x is the input, from x we get a result for the first layer's output A, then the first layer's output A will feed into the second layer, vice versa, until we get to the third layer with the neural output A, which actually is our network model output. Usually, calculating this place will stop, but for the training purpose, the output of the neural model will be fed into a cost function, which we see here. So we can see those. I just labeled the layer here, the layer 1, layer 2, layer 3, and also I labeled the cost function as a cost function layer. And which is needed during the training. When you use it, you don't see it anymore. And also we have the input. Some people call it input layer. Doesn't matter. I mean, if you understand what's going on, that'll be fine. And also the middle layer usually called hidden layer. Last layer, since it's equal to the output, sometimes we call it output layer. That's pretty much all the layers of the network structure. And then we will talk about the input first, from left to right. So input is very simple. So basically just x1 to 3 in this model, and it's x lowercase letter is a scalar. And usually we put all the scalar together, add a little arrow on top of it. We treat it as a vector. Most time, if don't mentioned, it's a column vector in the numerical model to be consistent. And from the left to right, next one we're talking about is the weight. Weight is actually one of the important parameters for the neural network model which need to be trained. And we can see there's a lot of superscript and subscript weight. Don't be afraid of it. We can explain these scripts. First, the superscript is basically just simple. It's layer. It doesn't mean power in the neural network model. Of course, when we talk about the transfer function, there could be power there. But here, anything notation for neural network model, the superscript is a layer. It's not power. That's what I need to clear. Then we can see there are two subscript here. One's I and there's a J. Just remember this way. This weight is to the S neuron of layer L, and the input is from the J's neuron of layer L minus 1. That's the convention of the weight scalar. And it has the most script for this variable. But if you can remember this, a lot of stuff will be very clear. Let's go through one example here. For example, this one is W sub 2 3 super 2, which means the 2, as we mentioned, it's a the superscript 2 is a layer 2, and we can see it's a weight to the second layer of the layer 2 are from the third neuron of the layer 1. So that's how we understand the weight. And usually for the purpose calculation, we put all the weight in a matrix for each layer. We call it weight matrix. So it's W superscript L. It's a weight matrix for layer L. So basically every layer has a weight matrix. And the next important parameter for the neural network model is bias. I didn't mark it in the joint. I don't want to make it too busy, but it's every neuron has a bias. So for example, this one, B sub I super L, basically means it's a bias of the ith neuron of layer L. And a lot of times, similarly, we will write the bias as a vector form. So basically, just the B super L and with a little arrowhead, which is treated as a vector for easy calculation. This is a B vector. It's a vector form of B. And after explain the input, weight, and the bias, we're going to start talking about the details of the neuron. So we'll start with, in order to explain the N and A, Y, and C, we will have a detailed neural model here. Although we just draw a simple circle with N and A inside it, actually there's a more detailed neural model, which we didn't use just because I don't want to make the network structure too complex. So basically, there's two portions of this neural model. And as you can see from the screen, it has a N part and it has a A part. The N part is a weighted linear combination of all the inputs and the bias, which you got N. And there's a F part, which is a nonlinear part. Then the net input function then got A, which is a neuron output. So the neuron has a perfectly combined the linear calculation and the nonlinear. Oh, I read it. Unlinear actually, nonlinear calculation together. So just explain the symbols here. So basically, N sub I super L basically just means the net input of S neuron of the layer L. And similarly, we will have the A sub I super L as the output of the ith neuron of layer L. And we can see the one good thing about the net input and output of neuron, you don't have one subscript instead of two, like the weight parameter. So the relationship between the light input and the output. Oh, here we will write. Usually we write as the light input and the output as a vector form. So similarly, each layer has one vector light input and one vector output. Similar to the before, we just put a little arrow on top of each letter. So the relationship between the neuron's output and the light input is A equal to F of N. So, and you can see actually the N, we already know N is a weighted combination of the output of the last layer. So this calculation can go on and on until the beginning of the input of the neural network model. And the relationship, as I just mentioned, is and the relationship between the relationship between, yeah, it's f. Why I need to mention here, f a lot of time is called f is called the activation function here, and you can choose f. And actually, that's one great advantage of neural network model, because you design the model, you can choose a different f for each model, even for each layer. And a lot of real world problem I faced before, you don't have this luxury to choose a function. So that's one thing good about neural network model. You choose function which is easy for your training. And the next one we will talk about the model output. So obviously A is the neurons output, and the Y is the model's output. And we can see actually the last layer of neurons output A is the model's output Y. So we just add a Y symbol to make clear it is the output. So it's similar. We put a small head on top of Y, just saying this estimation of the real output. So there'll be two head of Y, and if you write it in the vector form. And I just mentioned that in this case, the network amount output equal to the neuron output of the output layer. That's the output. We explained everything, almost everything from the left to right. There'll be the last layer, which is invisible to the user. It's just the training. When you're training a model, you need a last layer. It's called cost function, because you got estimation of the output Y. You want to compare to the real observation, real data you have, and then use that information to evaluate performance of your model. And the goal is minimize the difference between your estimation and the real world numbers. And basically, it's just pretty much because the annoying variables of the neural network model is weight for each layer and the bias for each layer. So pretty much it's a minimization problem, minimization optimization problem regard to the weight and the bias for each layer. And that's pretty much all the basic, most, I wouldn't say all, most basic notation of neural network model. And of course, there will be some new notations, and we will introduce them when we talk about uh, specific topics, for example, the backpropagation. And this pretty much that's it. In this short video, we demonstrate the network structure, and from left to right, we explain all the symbols, notations, and we showed the meaning of the superscript and subscript. And you can pause here to take a look to memorize these symbols, and which will be used in a future discussion. Thanks a lot for your time. Hope to see you in the next video. Bye.